that is, how do you find the angular momentum of a body which is in a translatory motion as well as rotatory motion about some axis or about some point. Let's understand this through by a few cases. So over here we have this disk which is along the y-axis about its center of mass. It is rotating with angular velocity omega in this direction. So angular velocity is this way, this y-axis. Let's say this is a disk of mass m and radius r. So that its moment of inertia about this axis, we know that is mr square by 2. So angular momentum is going to be about this, is going to be equal to I omega. That is I about cm into omega. It is going to be mr square by 2 into omega. So when it is moving in this direction by right hand thumb rule, the angular momentum direction vector is in the upward direction and upward direction vector is j cap. So it is L is I omega j cap. So L is mr square by 2 omega j cap. Now over here, this is a disk which is not rotating about its center of mass, but the whole thing is rotating about this z-axis. Let's say this is z-axis. So this disk is not rotating about this axis, but this is moving about this axis like this. It is not rotating about this axis. So it is only rotating about z-axis, and we have to find its angular momentum about this axis. So obviously, that is, we can directly use as L is equal to I omega. L is equal to I omega. Omega about this axis. What is that? That is suppose given as omega. And what about I? I is going to be this axis only, that is zz dash. So we can say that is L, angular momentum of this, which is this disk which is rotating with angular velocity omega about this axis, is going to be I omega. I about this axis we can use by parallax theorem, that is mr square by 2 ICM plus m into d square. We have done it, parallax theorem, into omega. And what is the direction? That is k vector, k cap. So this is going to be the angular momentum of this disk which is not rotating about its axis, but it is rotating with angular velocity omega in this direction. Coming to this, over here, once again this is a disk. We are looking from here, this is x, this is y. So in xy plane, suppose this is rotating with angular velocity omega and this is also moving this with a linear velocity v. We have to find its angular momentum about, let's say, about O. So now this angular momentum of this body, which is in rotation also about its own axis and translation also, so it is going to have two angular momentum. One is because of translation, the other is because of rotation. Let's write them in vector notation. So L about O, if we talk about, so one is because of translation, the other is because of rotation. And because of translation, obviously the mv vector is this way, linear vector is this way, this is position vector r at any moment, so this is angle. So r cross mv is certainly, it's going to be minus k cap. So this is going to be minus k cap. It is going to be minus k cap. That direction is going to be into the plane of the paper, because this x-axis, this y-axis, z-axis is perpendicular to the x and y-axis. So it is this way, it is going to be inwards, that is minus k cap. And what is that? That is, we say L translation plus L rotation. L translation is r cross mv, that is r is what? That is moment of momentum also, you can directly say. That is, this is momentum is mv into d, this is a d distance, moment of momentum, and direction is what? Direction is, we say, minus k cap, and rotation is L rotation about what? About its own axis only. This is rotating about its own axis. So it is going to be plus I. If this is C, center of mass is C, we call it a C. So IC into omega, and once again it is moving in this direction, so its angular momentum is once again into the plane of paper. So it is minus k cap. So this is angular momentum of this disk, which is lying in the plane xy axis about its own axis. It is moving with the angular velocity omega, and it is moving parallel to x-axis with the velocity v. This is the angular momentum in vector notation. Now coming over here, once again this is x-axis, this is y-axis, this is z-axis, and this is a disk which is rotating with angular velocity omega about the y-axis, and this is also translating in this direction also. Once again over here we say the body is in rotatory motion as well as translatory motion. So once again the angular momentum of this body about O is because of translation and also because of rotation. So L about O is equal to L because of translation plus L because of rotation. L because of translation is, so this is momentum mv into the distance between line of momentum and this axis d only. And what is the direction? On the same lines, it is minus k cap. It will be, that is into the plane of vapor, that is minus k cap plus angular momentum of this. Now this is rotating on the y-axis. I omega is this direction. So it is going to be IC. That is, IC is what? IC is mr square by 2. IC into omega. But IC into omega, now it is j cap. So it is going to be plus j cap. So this is L0. Over here we have k cap also. We have a j cap also. So this is how we find the angular momentum when the body is in translation also and when the body is in rotation also. So when we have to find the angular momentum of a body which is in translation also and which is also rotating also. So what we do is we find the angular momentum of the body because of its rotation, and during that time we are very clear, that is, it is going to be what is going to be its direction. And similarly, when we find the angular momentum of the body because of its translatory motion, over there also we are interested what is the direction of angular velocity. It is not, that is, we just add the magnitude. These are not the scalar quantities. So their direction, that is over here, if you see, that is one is comes out to be in minus k cap, the other comes in j cap. So we should be attentive while finding the direction of angular momentum because of translation and because of rotation, and we cannot simply algebraically add or subtract them.